All right, so this is the lesson for Unit 1, Lesson 7, which is modeling with functions. So, Unit 1, Lesson 7, modeling with functions. For this unit and this lesson, you'll learn about functions from formulas, functions from graph, functions from verbal descriptions, and functions from data. So basically, all we're doing is we're just combining everything that we've learned so far and putting them in Word problem format. So it's very similar to a lot of the stuff that we've already seen. So why? Using a function to model a variable under observation in terms of another variable often allows one to make predictions in practical situations, such as predicting the future growth of a business based on known data. So functions from formulas. Now that you have learned more about what functions are and how they behave, we want to return to the modeling theme of section 1.1. In that section, we stressed that one of the goals of the course was for students to become adept at using numerical, algebraic, and graphical models of the real world in order to solve problems. We now want to focus more precisely on modeling with functions. You have already seen quite a few formulas in the course of your education. Formulas involving two variable quantities always relate those variables implicitly, and quite often the formulas can be solved to give one variable explicitly as a function of the other. In this text, we will use a variety of formulas to pose and solve problems geometrically. Although we will not assume prior familiarity with those formulas that we borrow from other subject areas like physics or economics, we will assume familiarity with certain key formulas for mathematics. So things like the area of a rectangle or the area of a triangle or the area of a circle. So things along that line. So example 1, forming functions from formulas. Write the area A of a circle as a function of its radius r, diameter d, circumference c. So we know that the area of a function, we know the area of a circle is area equals pi r squared. So basically all this is asking us to do is solve for a specific thing. So it's asking us to solve for the radius. It's asking us to solve for the diameter, and it's asking us to solve for the circumference. So we know that the area of a circle is pi r squared, and we know that the circumference of a circle is that. We know the radius is d divided by 2, so the diameter divided by 2. And we also know that a circumference of a circle is circumference equals 2 pi r, or pi times the diameter, okay? So based off of this knowledge, we can use what we know basically to solve for something. So the first one we're solving for is the radius. All right, so write the area A of a circle as a function of its radius. Well, we already know that the area of a circle is pi r squared. So it already has radius in it, so that's all we have to do. So A equals pi r squared. For B, we're asking for the diameter. So write the area of a circle as a function of its diameter. So diameter, we said, was divided by 2 gives us the radius. So all we have to do is substitute that in for what we have. So again, A equals pi r squared. Substitute in the value for the radius of d divided by 2. Okay, so that gives us A equals pi d divided by 2 squared, which equals pi b squared, and then 2 squared is 4. So another way for us to rewrite this is a equals pi over 4 b squared. Again, I'm just looking for the area. All right, for C, I'm looking for the circumference. So since the circumference of a circle is equal to 2 pi r, we can solve for r. So we can plug it into our area formula. Okay. So that gives us C equals 2 pi r, which is going to give us C divided by 2 pi equals r, and then we substitute that into our area formula. So area equals pi r squared. So that's going to equal pi times c over 2 pi. So one of those pi's is going to cancel, so we're left with c over pi. Oh, I'm squaring that. Sorry. Squared. So this equals pi times c squared over 4 pi squared, which of course can be simplified. So this pi right here and one of these pi's can cancel out. So I'm going to be left with c squared over 4 pi. All right, example 2, a maximum value problem. A square of side x inches is cut out of each corner of an 8-inch by 15-inch piece of cardboard, and the sides are folded up to form an open-topped box. A, write the volume of the box as a function of x. B, find the domain of V as a function of x. Note that the model imposes restrictions on x. C, graph V as a function of x over the domain found in part B and use the maximum finder on your grapher to determine the maximum volume such a box can hold. And D, how big should the cutout squares be in order to produce the box of maximum volume? So, looking at this, okay, so if I'm looking at my book, all right, so this is what this looks like. This box is going to turn into this. So basically, I'm cutting out these little corners on the edge. And when I fold it up, if you were to put tape on it, it'll create that box. Okay? Just so we have an idea of what it looks like. So the box will have a base with sides of width 8 minus 2x. Okay, so remember what they told us up here is they're cutting the corner of an 8-inch by 15-inch. So we picked a side. We said width was the smaller size. You could use this as your length as well. It doesn't really matter. Okay, and we're subtracting 2 times the cutouts. So it's 8. That whole thing is 8 minus 2 times the squares that you cut out. Okay, so, and the length is 15 minus 2x. And because if you have 15 inches and you cut this off and you cut this off, those are 2. They're the same because they're squares. Okay. So if I have my box, right? This is a really awful box. I'm sorry. Okay. Okay. This whole side, this width is 8 inches, and this whole side is 15 inches minus this value of x and this value of x. Remember, because they're squares, they're going to be the same on both sides. Their length and width is the same. So 15 is just this whole side minus x. That's where I'm getting that 2x from. Same thing with the 8. This whole side is 8 minus x minus x. I'm trying to figure out what this value is right here. So that value is 8 minus 2x. Okay. Same with this value here. That value is 15 minus 2x. So that's where I'm getting those from. Then, because for A, I'm finding the volume of the box. Well, the volume is length times width times height, right? So we have the width and we have the length. We just need the height of a box. So the depth of the box, like if I fold the box up, it's going to be the depth of the box is x. So like if I were to fold this box, this side, remember those squares, they're still x by x. So that's where I'm getting the x value from. So therefore, v equals x times 8 minus 2x times 15 minus 2x. For b, find the domain of v as a function of x. So the formula for v is a polynomial with domain negative infinity to infinity. Okay. So when I graph this, like if I were to multiply this all the way through x times 8 minus 2x times 15 minus 2x, I would get a polynomial. I'm going to get a cubic polynomial, but I'm going to get a polynomial. And so if I looked at it and I graphed that, I know that cubic polynomials have a domain of negative infinity to positive infinity. So that's their x values. So no matter how far, it's going to go from negative to positive. I do know, however, that my depth can't be negative. And it can't be negative because if I had a negative volume, that means that I have a box that doesn't exist. I have to have a positive volume when I'm dealing with boxes. So the depth must be non-negative, as must the width of the base, 8 minus 2x. Together, these two restrictions yield a domain of 0 to 4. Okay, included. So if I substitute, so if I look for 8 minus 2x, 8 minus 2x equals 0, and I solve that, so that gives me negative 2x equals negative 8, and then x equals 4, because negative 8 divided by negative 2 is 4. That's where I get that 4 from, okay? So my depth can't be negative, and my width can't be negative. So the endpoints of a box with no volume, which is as mathematically feasible as other zero concepts. Okay, so basically I can't have, if I have a box with no volume, I don't have a box. Mathematically. Restrictions. C. C asks me to graph V as a function of X over the domain found in part B, and then use the matrix, the maximum finder on your grapher to determine the maximum value such as a box can hold. All right, so we're going to use Desmos for this. Okay. And I'm just going to use the formula that I've used before. So X times 8 minus 2X times 15 minus 2X. Okay, it does it for me, which is great. So I notice that 4 here. So if I zoom out, oh goodness. Okay, so if I zoom out here, here's my vertex up here. So that's where it's positive. Okay, and I'm going to restrict it to, there we go. So 0 is less than or equal to X, which is less than or equal to 4 because it's 0, 2, 4. So it includes all of these values from 0 to 4, okay? Because that's my restricted domain. So that's what this looks like. And then I can actually make it so it's a little easier to see. So my x-axis to be -1 to, let's say 5. Okay. So I can change this up a little bit. I just did that in the settings button. And all I did was I changed the x-axis to -1 to 5. So that way it was 1 after the 0 and 1 after the 4. 1 before the 0 and 1 after the 4. Just so I could see the graph a little bit easier. Okay, so this is what my graph looks like. All right, so this is C. So again, this graph, I can then find the maximum. Finder shows that the maximum occurs at the point. So if I'm looking at this graph, that's the maximum, 1.6, which is 5/3, and 90.741. So the maximum volume is about 90.74. That's cubic inches because that's what I'm measuring in. Okay, so I'm still measuring in volume. Okay. In order to get that maximum value, so remember the point was 5/3 and 90.74 cubic inches. So in order to get that maximum volume, the sides of the squares would need to be the value of X at the maximum point, which is 5/3. Okay, so basically that point, that maximum point tells you your X value, which we were saying is the side of the squares, and your Y value, which is the volume of the box. Okay, so when I set up this function, Y equals X times 8 minus 2X times 15 minus 2X, I was saying the volume, our Y value, which is 90.74, equals your X value, 5/3, and that will give you your highest volume or a volume depending on your values between 0 and 4. Okay. So if you have a value of 0, like if you don't cut anything out, you don't have a box. If you have a value of 4, you don't have a width, okay? Which means you don't have a box. So, and it doesn't hold anything, okay? Functions from graphs. When thinking graphically becomes a genuine part of your problem-solving strategy, it is sometimes actually easier to start with the graphical model than it is to go straight to the algebra formula. You don't have to, of course. The graph provides valuable information about the function. So example 3, protecting an antenna. A small satellite dish is packaged with a cardboard cylinder for protection. The parabolic dish is 24 inches in diameter and 6 inches deep, and the diameter of the cardboard cylinder is 12 inches. How tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish? So I can solve this algebraically. Okay. You can also see, so the diagram in figure 1.82a showing the cross-section of this three-dimensional problem is also a two-dimensional graph of a quadratic function. So if you look at it, that's what that looks like. So again, it's a parabolic function, which means it looks like a U. We can transform a basic function of y equals x squared. Okay, so we can transform a basic function of y equals x squared, because again, it looks like a parabolic function, with a vertical shrink so that it goes through the points 12, 6 and negative 12, 6. Okay. And I got those points directly from the graph that they showed us. So the graph that they showed us went through points negative 12, 6 and 12, 6. Okay. So this produces a graph of the parabola in the coordinate plane. So when I got those, let me show you in the picture. So I got those from this graph right here. So that graph is 24 long and 6 high. Okay. So that's where I got my point. So if I were to just cut it in half, that's my 0 point. So it's 12 from each side. So that 24 is split in half. So that's where I get negative 12, 6 and positive 12, 6. So that's where I get those values from, just so we know, because the 24 is across. Okay. So from here, I'm finding the vertical shrink, which is y equals kx squared, where k is that vertical shrink. So 6 is one of my y values, equals k plus or minus 12 squared. Okay. So when I solve, I get k equals 6 over 144, which simplifies to 1 over 24. Therefore, y equals 1/24 x squared. We find the height of the cardboard cylinder. We first find the y coordinate of the parabola, 6 inches from the center. That is when x equals 6. I just substitute that value in. So into my formula, so y equals 1/24 times 6 squared, and that's going to give me 1/24 times 36, which equals 1.5. From that point to the top of the dish is 6 minus 1.5, or 4.5 inches. Remember, the diameter is only 6 inches deep, and the diameter of the cardboard is 12 inches. So although example 3 serves nicely as a functions from graphs example, it is also an example of a function that must be constructed by gathering relevant information from a verbal description and putting it together in the right way. People who do mathematics for a living are accustomed to confronting the challenge regularly as a necessary first step in modeling the real world. In honor of its importance, we have saved it until last to close out this chapter in style. Functions from verbal descriptions. There is no fail-safe way to form a function from a verbal description. It can be hard work, frequently a good deal harder than the mathematics required to solve the problem once the function's been found. The 4-step problem-solving process in section 1.1 gives you several valuable tips, perhaps the most important of which is to read the problem carefully. Understanding what the words say is critical if you hope to model the situation they describe. Example 4, finding the model and solving. Grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. If the cone is 1 foot tall now, how tall will it be in an hour? Okay. So, a couple of things that I notice. They're saying the height of the cone always remains equal to its radius. So if it's 1 foot tall, that means its radius is 1 foot, which means its diameter is 2 feet. Okay. I want to know how tall it'll be in an hour. And I also know that the grain's coming out of the hole at 8 cubic inches per minute. That means if it's coming out at 8 cubic inches per minute for an hour, I need to multiply that by 60. So I know I need to multiply 8 by 60 in order to figure out how much grain has come out within that hour to start with. All right, so reading the problem carefully, we realize that the formula for the volume of the cone is needed. So the formula is V equals 1/3 pi r squared times the height. A careful reading also reveals that the height and the radius are always equal. So we can get volume directly as a function of height by saying V equals 1/3 pi height cubed. Okay, so we said that radius and height are the same thing. They're equal to each other. When r is 1, height is 1. So I'm just saying 1, in this case, if I use 1, radius times height is 1 times 1 times 1. So I can just combine those, and since they're the same, we have 3 of them, h cubed. Okay. So when h equals 12 inches, okay, so remember foot to inches. When h equals 12 inches, 1 foot equals 12 inches. The volume is V equals I over 3 V equals 1/3 times pi times 3 cubed, okay, which equals 576 pi inches cubed. So 3 cubed is 27. Oh, it's 12, not 3, sorry. 12 cubed is 576. 12 cubed is not 576. 12 cubed is 1,728 divided by 3 gives me the 576. Okay, so 12 cubed divided by, or times 1/3, which is really divided by 3, gives me the 576. The pi comes along for the ride. So an hour later, okay, because right, so that's where it starts. An hour later, the volume will have grown by 60 minutes times 8 inches, 8 cubic inches per minute, equals 480 cubic inches. So the total volume of the pile at that point will be 576 pi plus 480 inches cubed. Finally, we use the volume formula once again to solve for our height of h. So I have 1/3 pi h cubed equals 576 pi plus 480, okay? Because we found the volume originally, and then we found how much the volume grew within an hour. It grew 480 cubic inches in that hour. So we're adding the original volume plus the amount that it grew within that hour, and we're going to solve for the height so we can find how tall the cone actually is. Okay, so when I do this, I'm going to divide both sides by 1/3. Okay. Actually, I'm going to make this bigger so it's easier to see. So we're going to divide by 1/3. So 1/3 pi h cubed. That we're going to fraction 1/3 equals 576 pi plus 480 divided by 1/3. Okay. The 1/3 will cancel out here. So on this side, I'm left with pi h cubed equals, over here, change the division to a multiplication sign, flip. So I'm multiplying by 3. So 3 times 576 pi plus 480. Oops. Okay. Then I'm going to divide both sides by pi. Okay. 576 pi plus 480 divided by pi. Okay. So when I do this, and then I'm going to take the cube root. So that gives me cube root of h cubed equals the cube root of 3 over 576 pi plus 480 over pi. Okay. Okay. So when I do that, and I simplify it and I just put it in my calculator. So cube root of 3 times 576 pi plus 480. Yes, you can absolutely multiply the 3 through. Yes, you can just figure out what that is with the pi. You can absolutely do that. You're going to get h is approximately 12.98 inches. All right, example 5, letting units work for you. How many rotations does a 15-inch radius tire make per second on a sport utility vehicle traveling 70 miles per hour? So a rotation of a tire, we're talking about a perimeter. Okay, so we're talking about the perimeter of the tire. So we need to find the circumference of the tire. Okay, circumference is C equals 2 pi r. So that equals 2 times pi times 15, which equals 30 pi inches. So this means that one rotation equals 30 pi. From this point, we proceed by converting miles per hour to rotations per second by a series of conversion factors. That are really factors of 1. So I have 70 miles over 1 hour times 1 hour over 60 minutes times 1 minute over 60 seconds. Okay, so notice I'm just working on hours. Okay, so I know 70 miles per hour. So I'm going miles per hour to rotations per second. So I need to change hours to seconds. So there's 60 minutes in an hour and there's 60 seconds in a minute. Okay. You can also skip these two. It's 3,600 to go straight. We're just going to type them all out though. Okay. There are also 5,280 feet in 1 mile. 5,280 feet in 1 mile. Okay. Times 12 inches in 1 foot times 1 rotation in 30 pi inches. So basically I'm getting to that point where I'm going from miles per hour to rotations per second. Okay. And I know that my rotation's in inches. So 1 rotation is 30 inches. I'm still dealing with the circumference. So what happens is hours cancels out, minutes cancel out. I'm left with seconds. Miles cancels out, feet cancels out, inches cancel out. I'm left with rotations per second when I multiply this through. Okay, so now all I'm doing is I'm multiplying straight across. So 70, so when I write this, 70 times 1 times 1 times 5,280 times 12 times 1 over 1 times 60 times 60 times 1 times 1 times 30 pi. Okay, this is going to equal approximately 13.07 rotations per second. Functions from data. In this course, we will use the following three-step strategy to construct functions from data. Constructing a function from data. Given a set of data points of the form x comma y, to construct a formula that approximates y as a function of x. Make a scatter plot of the data points. The points do not need to pass the vertical line test. Determine from the shape of the plot whether the points seem to follow the graph of a familiar type of function. It's a line, a parabola, a cubic, a quadratic, a sine curve, anything along those lines. So you're looking for a graph that kind of looks familiar to you. Transform a basic function of that line, of that type of line to best, or type of graph, to best fit the points as closely as possible. Step 3 might seem like a lot of work, and for earlier generations, it certainly was. It required all of the tricks of section 1.6 and then some. We, however, will gratefully use technology to do this curve fitting step for us, as shown in example 6. Curve fitting with technology. Table 1.12, which is right here, records the low and high daily temperatures in degrees Fahrenheit observed on 9/9/1999, so September 9th, 1999, in 20 major American cities. Find a function that approximates the high temperature y as a function of a low temperature x. Use this function to predict the high temperature that day for Madison, Wisconsin, given that the low is 46. Okay, so here's all my functions. Yay. All right, so we can notice, so first off, I want to graph these points. So I'm going to get my calculator. All right. This one's not in Spanish this time, just so we know. Okay, so you're going to hit the blue button, which is the second button, and then the stat button right here. Okay, that's going to take you to a set of lists. So you're going to put all your x values in list 1 and all your y values in list 2. So I'm going to go ahead and do my x values. Remember, your x values are your lows for your city. So I'm going to hit 1. It's going to take me to my list. That actually shows me my list. Okay. So you want to hit stat. That's where your list lives, just so you know. So stat, in order to change the list, you have to hit stat first. Okay. Then it gives you this menu. We want to go for number 1, which says edit. So just click on number 1. It's going to give you this formula. Okay. I already have a list in here. This is for something else. So you can delete your list. That's fine. You can do it by hand, or there's another way to do it, and I can show you that too. So if I want to delete my list, again, I go to stat. Okay. Then I go to 4, which says clear list. Then I go to second, and then stat again. So I can pick my list. Now I'm going to pick 1. And then I hit the comma button because I can do multiple lists at the same time. And then I do second stat 2. and then I just hit enter and it clears my list for me. So now when I go back and I look at this, I'm going to have blank list. So I'm going to do the same thing. I'm going to hit stat first, okay? And then I'm going to hit 1 for edit, okay? Now I have nothing there. Yay, clear lists. Okay, so now I'm going to go through and I'm going to enter each of my lists. Okay, so low are going to be your list, first list. And you just, so like the first one is 70. So I do 70, enter, 62, enter, 52, enter, so on and so forth. Okay, for L1. All right, so I got to the bottom of my list. Now I'm going to hit on my calculator, it's the gray button, the gray over button. So I go to list 2 and I'm going to enter all of my high values, which are my Y values. Okay. You should end up with 2 lists that are equal length. Okay. So now all I'm going to do is I'm going to graph these points. So I go to second, and then I hit the Y equals button at the top. Takes me to this. Okay. This says off. So for 1, and I want to hit enter. And then where it's a little blinky to on, I want to hit enter. My X list is my list 1. My Y list is my list 2. Yes, cool, wonderful. You can change so it has pluses or little dots, however you would like to make it look. But I just want a scatter plot. So I'm good with that. My type's already set up as a scatter plot. And then I hit the graph button. We probably have to readjust the windows. So I go to, notice there's nothing there. So I'm going to hit window right here, window button. Okay. And my lowest value, 52 for X. So I probably want to do, let's go 0. And then my highest value looks like 76. Nope, 82. So we'll say 100. And I want to do 10 as my scale. Okay, and I'm going to do the same thing with my Y. So 0, 2, and my max for my 0 is 92. 106. Probably should do more than that. We'll do 115 for that. Ooh, that was way too much. Delete that 0. We're going to go by a factor of 10. Okay, so that's what mine looks like. So X equals 0. So my minimum, I'm going to start my graph at 0, and I'm going to go to 100 with values increments of 10. And then my Y value, I'm going to start at 0 and go to 115, again, with increments of 10. Actually, I should do 120. We're going to change that. 120, because then my life will be nicer. Now I hit graph. Now look at that. Okay, so there's my lovely little graph. Okay, so of course this is a scatter plot. Of course you can change this and make it bigger and blah and all of that stuff. So you just have to go back to that window and basically recalculate. Like if I wanted to go, okay, well, most of my graphs right there. So if I wanted to start at 40 and go to 100, and I wanted to start at 40 and go to 110. Okay, so notice my graph's a little bit more. It's still the same exact type of points, but this way you at least get to see more of the data a little bit closer. So all of this data, it's not like forming any sort of crazy type of quadratic or cubic or sine curve or anything like that. It literally looks like a line. I could draw a line through there and probably hit the majority of my points. Now, you can do this by hand, or you can use this calculator. Okay, so you're basically going to have a line of best fit. It's called a regression line. So if I go to So if I go to stat, so again, I hit my stat button. This comes up again. I'm going to go over where it says calculate. Okay, C-A-L-C. And I'm going to scroll all the way down to number 8. Okay. I'm going to hit enter. See, it says like nice, pretty, A plus BX. And I'm going to hit enter. And it's going to give it for me. Okay. So that gives me my values for A and for B. A in this case is 23.014, just rounded to 23. And B is 0.9698. Again, I'm going to round to 0.97. Make my life easier. Okay. So then I just substitute those values in. It makes my life easier. So come back here. Okay. So in general, you might have to play around with this to kind of adjust it to what you want to see. But a good rule of thumb is you need to at least include, find your lowest X value and find your highest X value, and that's your min and max. Add, 5, add 2 points to each, or subtract 2 points from each. Same thing with your Y values. Okay. So then you're going to hit graph. Okay. You can adjust from there. Then stat. Move over to calc. Enter 8. Enter. So this gives you the linear regression. So A plus BX, and in this case, A equals 23 and B equals 0.97. I rounded to 2 decimal places. Okay. So that gives us our line. So Y equals 23 plus 0.97 times X. Okay. They did ask us as the second part is use this function to predict the high temperature that day for Madison, Wisconsin, given that the low was 46. So we're going to substitute 46 in for X and solve for Y. Because remember, Y is our high temperature, so 23 plus 0.97 times my low temperature in Madison was 46. Okay, and this gives us 0.97 times 46 is 44.62. 62 plus 23 is 67.62. So the high temperature is around, or should be around 67.62 if this model holds. Okay. Professional statisticians would be quick to point out that this function should not be trusted as a model for all cities, despite the fairly successful prediction for Madison. For example, the prediction for San Francisco with a low of 54 and a high of 64 is off by more than 11 degrees. The effectiveness of a data-based model is highly dependent on the number of data points and on the way that they were selected. The functions we construct from data in this text should be analyzed for how well they model the data, not for how well they modeled the larger population from which the data came. In addition to lines, we can model scatter plots with several other curves by choosing the appropriate regression option on a calculator or computer. These graphs are only examples, as they can vary in shape and orientation. For example, any of the curves could appear upside down. The grapher uses various strategies to fit these curves to the data, most of them based on combining function composition with linear regression. Depending on the regression type, the grapher may display a number R called the correlation coefficient. Okay. or a number r squared or r squared, called the coefficient of determination. In either case, a useful rule of thumb is that the closer the absolute value of this number is to 1, the better the curve fits the data. It is unrealistic to expect a regression curve to fit data from the real world perfectly. So statisticians do not expect to see r squared or r squared equal to 1. However, if the ordered pairs are actually derived from a function defined by one of the regression types, the calculator will confirm that. So you have this page in your book 140, and it's got all these different types of functions and kind of what they look like. And that is the end of Unit 1, Lesson 7.